This is part 2 of video 1, graphing the functions. And we're going to look at how to graph the cosine function. The graph of y equals cosine x has the same general shape as the graph of sine x. We can sketch the graph of y equals cosine x by making a table of convenient values. And again, let's use the multiples of 5/4. 5/4, pi/2, 3/4, and so on. And we will find the values corresponding to the values of x. For example, when x is pi/4, or our angle pi/4, the cosine of x, remember cosine x is represented by x coordinate, angle pi/4 will give us x that is equal to 0. 3pi/4 will give us the x that is equal to negative square root of 2/2. So by plotting the points, we obtain the graph of shape of the cosine function. We can also generate the graph of cosine function using the unit circle, just as we did with the sine function. By definition 3, if the point xy is t units from 1, 0 along the circumference of the unit circle, then cosine t equals x. We start at the point 1, 0 and travel once around the unit circle, keeping track of the x coordinates of the point, then that are t units from 1, 0. So we travel along the unit circle and we notice the coordinates of the x values. Extending the graph from 0 to pi to further one more period to the right and one more period to the left, we can see that this figure indicates the period, amplitude, and range of the cosine functions are the same as for the sine function. The zeros, or x-intercepts, of y equals cosine x are the values that are pi/2 plus k pi for any integer k, just the same as if in the sine function. Now let's look at a tangent graph. Again, let's make a table of values where x equals 0, pi/4, pi/3, pi/2, and 2pi/3, 3pi/4, and pi. And we can find the sine function, the tangent x is equal y/x. So if you look at the unit circle, angle is pi/4, tangent of pi/4 is y/x, which is square root of 2/2 divided by square root of 2/2, which is 1. Then we go to x, our angle is pi/3. Pi/3 is square root of. So we know that the tangent function will be undefined at x equals pi/2. Because at pi/2, our y is 1, our x is 0, while 1 divided by 0 will give us undefined value. And at pi, pi tangent is equal to 0 because y coordinate is 0 divided by -1 is equal to 0. So here's our graph of the tangent function. Because y equals tangent x is undefined at x of pi over 2, there's no point on the graph with an x coordinate of pi over 2. To help us remember this, we have drawn a dotted vertical line through x equal pi over 2. This vertical line is called asymptote. The graph will never cross or touch this line. If we were to calculate values of tangent x when x is very close to pi or very close to 90 degrees in the degree mode, we would find that tangent x would become very, very large. It will go as close to this line, as close to asymptote as possible, but will never touch it, so it will reach the infinity. It will get larger and larger as x is getting close to pi over 2. And if we were to calculate values of tangent x when x is very close to pi over 2 or very close to 90 degree mode, we would find that tangent x would become very large for values of x just to the left of the asymptote and very large in the negative direction for the values x just to the right of the asymptote. Extending the graph to the right of pi and to the left of 0, we obtain the graph shown in the figure 11. As this drawing indicates, the period of y equals tangent x is pi, because it goes from pi over 2 to 3 pi over 2, which is pi. The tangent function has no amplitude because there is no largest or smallest value of y on the graph of y equals tangent x. For this same reason, the range of the tangent function is all real numbers. Now that we have the graph of the sine, cosine, and tangent functions, we can use the reciprocal identities to sketch the graph of the remaining 3 trigonometric functions. Let's look at the cosecant function. To sketch the graph of the cosecant function, we will use the graph of the sine function because cosecant of x is 1 divided by sine of x. So for x equals 0, sine x is 0. For the cosecant, and cosecant x is 1 over sine x. Well, 1 over 0 is undefined. When x equals pi over 4, sine of pi over 4 is 1 over square root of 2 or square root of 2 over 2. 1 divided by 1 over square root of 2 is square root of 2 or approximately 1.4. Sine of pi over 2 is 1. 1 divided by 1 is 1. And so on. So here is the graph. The blue graph represents the sine function, and the red graphs represent the cosecant function. The cosecant function will be undefined whenever the sine function is 0, so that y equals cosecant x has vertical asymptotes at the values x equals k pi for any k. Because y equals sine x repeats every 2 pi, so do the reciprocals of sine x, so the period of y equals cosecant x is also 2 pi. As was the case with the tangent, there is no amplitude. Here's the graph of the y equals cotangent x. The period is also, as with the tangent function, is pi. There is no amplitude because the range is also from negative infinity to positive infinity. Now let's look at even and odd functions. What do we call even function? A function is called even function if f of negative x is equal f of x for all x in the domain of f. The graph of an even function is symmetric about the y-axis. An even function is a function for which replacing x with a negative x leaves the expression that defines the function unchanged. If a function is even, then every time the point xy is on the graph, so is the point negative xy. And an odd function is a function for which f of negative x equals negative f of x for all x in the domain of f. The graph of an odd function is symmetric about the origin. The odd function is a function for which replacing x with a negative x changes the sign of the expression that defines the function. So if a function is odd, then every time the point xy is on the graph, so is the point negative x, negative y. That sine is an odd function and cosine is an even function. We can use our ratio and reciprocal identities to find which of the other trigonometric functions are even and which are odd. For example, let's look at the cosecant. Cosecant is an odd function. Let's show that. We will need to prove that cosecant of negative theta is negative cosecant of theta. That is, we must turn cosecant of negative theta into negative cosecant of theta. So let's look at the steps. Cosecant of negative theta, we know by reciprocal identity that is 1 over sine of negative theta. Well, sine is an odd function, so sine of negative theta is negative sine of theta. From the algebra knowledge, we know that negative in the denominator can be moved into negative for the whole fraction. So negative 1 over sine theta is equal to negative cosine. Because the sine function is odd, we can see from the drawing that the graph of 1 equals sine x is symmetric about the origin. On the other hand, the cosine function is even, so the graph of y equals cosine x is symmetric about the y-axis, meaning that if we fold the graph about the y-axis, it will be symmetric on both sides. We summarize the nature of all 6 trigonometric functions for easy reference. Even functions are cosine and secant. Odd functions, sine, cosecant, tangent, and cotangent. Even functions are symmetric about the y-axis, and odd functions are symmetric about the origin. Now let's look at the examples and use the even and odd function relationship to find exact values for each of the following. Cosine of negative 2 pi over 3, we'll need to find the value, and cosecant of negative 225 degrees. So the first one is cosine of negative 2 pi over 3. Well, we know that cosine is an even function, so cosine of negative 2 pi over 3 is equal to cosine of 2 pi over 3, which is, from the unit circle, cosine of 2 pi over 3 is equal to negative 1/2. Now the next one is cosecant of negative 225 degrees. Cosecant is 1 over sine, so we use reciprocal identity to rewrite cosecant of negative 225 degrees to 1 over sine of negative 225 degrees, which is equal to 1 over negative sine of 225 degrees, because we know that sine is an odd function. From the unit circle, 225 degrees sine of 225 degrees is equal negative square root of 2 over 2, or negative 1 over square root of 2. Negative negative will give us positive. 1 divided by 1 over square root of 2 is square root of 2.